Perfect. So today I'm going to tell you a little bit about the research that I do, and mostly about the motivation of what we do, or why we're trying to develop the type of gamma ray detectors that we develop in my lab. And to do that, we'll talk a little bit about what are the constituents of matter when we are looking at the universe, what we think the universe is made of, what are the fundamental building blocks of the things that we see, and also for the things that we know are there but we don't see, which is what we call dark matter. And then we'll tell a little bit about what tools can we use to try to find out what this dark matter is. So I'll just start with a picture of one of my favorite places, which is Thousand Island Lake in Sierra Nevada. So we were hiking there in 2011, and I took this photo. And then if I look at it, so of course, with a physicist mindset, you kind of want to know what everything is made of. So what makes this landscape so beautiful? Well, we have plants, and plants are mostly cellulose, it's wood, so it's a complex molecule. Then we see that the leaves are green, and that's because they have chlorophyll, and chlorophyll is again a complex molecule that absorbs red light and absorbs blue light but reflects green light, so that's why these leaves look green. And then of course there's the beautiful mountains of Sierra Nevada, which are mostly made of granite, and granite is basically silicon oxide, which crystallizes in these ways that makes it hard, so that they erode only slowly, and they make these beautiful shapes. And they also have potassium oxide, aluminum oxide, and then of course there's the clouds, there's the snow, there's the lakes, which are made of water, and we know that water is basically two hydrogen atoms and one oxygen atom. Yeah, so there's someone in the chat. If you don't hear me, you should let me know, because we're already going on. So we see all this landscape. We can kind of try to break it down into building blocks, but we know that at fundamental level, there are more layers to this. So if we zoom into the water molecule that we have in here, what is this water molecule made of, and how are water molecules held together at all? So we know that a water molecule has two hydrogen atoms and one oxygen atom. And if I look at the oxygen atom, if we zoom in, what would we see? So we would see that the oxygen atom has 8 electrons, and these electrons are tiny fundamental particles. So as far as we know, the electrons don't have an internal structure. Electrons are elementary particles. They cannot be broken down into smaller pieces, and they have negative electric charge. And these electrons are somehow bound to a heavier nucleus that has positive charge. So what is keeping the oxygen atom? What is keeping it together? It's basically what we call the electromagnetic force. So we know that electric charges, they can be either positive or they can be negative. And we know that when two charges of the opposite sign are together, they are attracted to each other. So there's a force that makes the electron want to get closer, if you want, to the nucleus, and there's a force that attracts the nucleus to the electrons, if you want. So if I look at the hydrogen atoms, I know that the hydrogen atoms, they only have one electron, and they also have a positively charged nucleus. And then how come that this water molecule is held together is again by electromagnetic force, by the attraction of electric charges. So if you see here, we kind of say that the electrons in oxygen, they are organized in two shells. In the first shell, there's room, if you want, for 2 electrons. But in the outer shell, there's actually room for 8 electrons, and there's only 6 in oxygen. So when you have a water molecule, the hydrogen electron, the electron from this hydrogen is shared with this oxygen, and the electron from this hydrogen is shared with the oxygen, so that it completes this shell of 8 electrons and makes it a lot more stable. So we could say that what is holding atoms together and what's holding molecules together, it's basically the electromagnetic force, the attraction and repulsion of electric charges. Do we have any questions so far? If you have a question, just unmute yourself and speak up. So let's try to zoom further in, because we know that atoms are not fundamental particles. Atoms can be broken down into smaller pieces that can be broken down in electrons, and we can separate the electrons from the nucleus. The electrons are fundamental building blocks as far as we know, but the nucleus is not. If I look at the nucleus of an oxygen atom, I would see that it has an internal structure. So what is this internal structure made of? Well, we say that we know that the nucleus of oxygen is positively charged. And the reason why it's positively charged, it's because it has 8 protons. So the protons, they are more massive than, about 2,000 times more massive than the electrons. So they are bigger, more massive. And they have a positive charge. They are positively charged. But now when we think, well, what can keep the nucleus together? Because we know that all these protons are basically held together in the nucleus. If we understand electromagnetic forces as a force that makes 2 charges of the same sign, or 2 charges of opposite sign attract each other and 2 charges of the same sign repel each other. Now here I have a whole bunch of charges of the same sign, a whole bunch of protons that are held very close together. And we know that the electrostatic force would want these protons to move away from each other, right? So there has to be another force that, at least at these small distances, is stronger than the electrostatic force. And this force is what we call the strong nuclear force. So the strong nuclear force, as we say, is stronger than electromagnetism, because all these protons, they want to fly away from each other if it was only because of the electrostatic force. But when they are close together, they feel the strong nuclear force, and that's what's keeping these atomic nucleus together. We also know that the proton is not the only thing that's inside of a nucleus. We know that there's also neutrons. And well, this arrow went to the wrong place. It should have gone to a neutron. So neutrons are particles that have very similar mass as the protons, but they have no electric charge. They have no charge at all. But they feel, or they react to the strong nuclear force. So they are in a way acting as a glue to keep all these protons together. So we could say, well, now we've got it. We have all the fundamental building blocks of matter, but we know that protons and neutrons are actually not fundamental particles. They are not elementary particles. They can be broken down into pieces to some level. So if I look at a proton, we can see, doing high energy physics experiments, doing basically smashing protons into each other, we can see that they have an internal structure. And this internal structure is made so that a proton is made of 2 quarks that we call up quarks, and they have a charge of 2/3. And then we have a down quark that has a charge of -1/3. And basically these quarks, they interact with each other by exchanging other lighter particles that we call gluons. And these gluons are basically the carriers of this strong nuclear force. So a proton is basically 2 up quarks and 1 down quark. And if I add the charges, I would say, well, 2/3 plus 2/3 but -1/3 gives me a charge of 1, +1, which is what I expect, which is what I want the proton to be. And then we see that the neutrons, they are basically 2 down quarks and 1 up quark. So if I add -1/3 -1/3 plus 2/3, I get a charge of 0. which is the charge that we know the neutron has. So here, basically, at this level, this is the smallest level that we've been able to break things down. So in a way, particle physicists, they are a little bit like little kids. They just smash things and see what pieces come out. And this is as small of a piece of matter that we've been able to see. So as far as we know, the up quark and the down quark, they don't have an internal structure. They cannot be broken down into pieces. Maybe maybe we will find some at some point in the future that they do have structure, but as far as we know, those are the fundamental building blocks of nuclei, and those are the ones that make up the matter content, the material that we see around. Are there any questions so far?
Oh, there was one question from Joe about does each electron only hold the same amount of electrons for each element, or is the number unique to each element?
Okay, so if we look here at this oxygen atom, so atoms generally they are neutrally charged. So they have the same number of negative charges in form of electrons as they have in positive charges in the nucleus, right? So whenever we say oxygen, oxygen means that the nucleus has 8 protons, right? So it has a charge of +8 in the nucleus. Now, unless we do something kind of nasty to this atom by basically pulling an electron out of it, these atoms will tend to be neutral. So that means that there's room or that this atom will have 8 electrons. Now, when we draw these circles here, this is basically, if you want, the way that electrons want to organize themselves in this atom. So we know that this first energy level, if you want, it has room for 2 electrons, and the outer energy level, in principle, would have room for 8 electrons, but it will only have 8 electrons if there are 2 more protons in here. So basically, to answer your question, the number of electrons that you see in an atom is always it always depends on how many protons there are in the nucleus. But the way these rings are organized, this is not specific for any element, but they all tend to organize themselves in the same shells with the same number of room or electron places for electrons at each shell. I forget. I'm not very good at chemistry. I forget which one is element number 10, but. Does anyone remember? I'm sure someone will know. It's neon, right? Is it neon? I might be lying.
I think that's right. Yeah.
So if we had a neon atom here, assuming the neon is number 10, we would have 10 protons in the nucleus, and then we would have 2 more electrons that would complete the second shell. And if we were to add up 1 more charge, which I forgot what goes after neon, then the next electron would need to be placed in the third. Would start filling up the third layer. Does that answer the question more or less? Okay. So, oh yeah, sodium is 11. Thanks. Perfect. So if we now try to say, well, so can we build everything that we see with just electrons, up quarks and down quarks, and then these force carriers, gluons, and also the electromagnetic force carrier, which is photon, which is basically light. So can we build everything that we see with just this handful of particles? And the answer is largely yes. Basically everything that we see is just made of up quarks, down quarks, these gluons, and electrons and photons. But when we do these experiments like little kids, when we try to smash particles onto each other and see what comes out, we see that even though we don't need new particles to explain what we see in nature, what we see when we walk around the street, we know that there are more particles that that are produced when you basically have a system that has enough energy. So what we were saying is that the up quark here, the down quark here, and the electron, together with the gluon here and the photon here, that basically builds all, that's all we need to build everything that we see around. But we know that the up quark and the down quark have a pair of cousins or brothers, if you want, which are the charm and the strange quark. They have the same charges, but they are more massive. And then there's even a third generation that even has more mass, which is the bottom and the top quark. So basically, these quarks that you see here, they have very similar properties to the up and down quark, but they are just more massive. The top quark was the last one to be discovered, and it has basically the same mass as a gold nucleus. It's a huge particle, if you want, and it's an elementary particle as far as we know. But these particles, they tend to be very unstable, and they cannot really be isolated. So whenever you try to pull an up quark or a down quark from a nucleus, it immediately wants to put itself together into protons and neutrons and other particles. The same happens with the electron. The electron has also more massive cousin, if you want, which is the muon, and there's even a more massive cousin of them, which is the tau lepton. And there's also lighter and neutrally charged particles that are kind of also related to electrons, which are the neutrinos. We also see that there's another force that plays a role in nature being as we see it. So we've talked about the electrostatic force or the electromagnetic force, which is the force that attracts or repels electric charges. We've talked about the strong nuclear force that keeps the nucleus together, but there's also the weak force, which is mediated by these particles that basically appears usually whenever there's nuclear reactions or nuclear decay inside of a nucleus. It's the responsible for most of the nuclear decay that we see. And then we know that a couple of years ago, the Higgs boson was discovered. And the Higgs boson is basically a particle that, if you want, helps or gives mass to all the particles that we see here. So this picture that we see here is what we would call the standard model of particle physics. These are all the particles and all the interactions that we need to explain all the possible reactions that we see when we put very energetic particles and smash them together. So is this all that there is? And the answer is, well, not quite. There's still a missing part to this, which is that in experiments that involved cosmic rays, people started seeing particles that were not in this picture, in this standard model. So what we see here is basically, this is a picture from what we call a bubble chamber. And basically a bubble chamber is just a vessel, if you want, where you can take pictures. And these pictures, they show the tracks of particles inside of this chamber. And these chambers, they usually have magnetic fields. And we know, for instance, here, we know that this track here is the track of an electron. Why we know it's the track of an electron? We know it's the track of an electron because we know that negatively charged particles in this bubble chamber, they will go clockwise, they will circle clockwise. So that's what we see here. We see an electron that's circling clockwise. And we know it's an electron because basically the way these particles lose energy, or it depends on their mass. So we know that an electron circles this way because it has a very small mass. So it loses its energy, if you want, relatively fast. But in these bubble chamber pictures, there was a second type of particle that started showing up. And as we see here, this particle is circling in the opposite direction of the electron. and that means that it has the opposite charge as the electron. But we know it's not a proton, because a proton would not have the same radius. It would basically lose energy in a different way. So we know that this track here is produced by a particle that has the same mass as the electron, but it has positive electric charge instead of negative electric charge. So this is what we call antimatter. And antimatter is basically, again, another generation, if you want, of if you want, second cousins to the particles that we just talked about, that have the same properties as the normal matter. So the electron and the positron, they have the same mass, but they have opposite charges. And for each particle of on our family picture of the standard model, there's an antiparticle that has, again, the same properties, but different, but opposite charge. So we know that, again, in order to explain everything that we see, we need all these particles in the standard model, but we know that all these particles, they have antiparticles as well. And so here, again, the way we generate these antiparticles is by throwing very energetic protons and producing producing a photon, and this photon has a high energy and has enough energy to produce a pair of an electron and a positron. So basically, you can build very large machines that can produce antimatter, but you can also go to Schnucks and buy yourself some antimatter in the form of a banana. So why would a banana have any amount of antimatter? So we know that a banana has about half a gram of potassium, and a little bit of the potassium that's found in nature is radioactive. And this radioactive potassium, what it does is it basically exchanges a neutron in its nucleus by a proton. Exchanges a proton for a neutron, and it produces a positron. And this positron immediately disappears, because what we know about antimatter is that when an antiparticle meets its partner, its particle, it basically annihilates. So that's why we don't see much antimatter around, because if there was any antimatter, it would immediately disappear by interacting with matter. So yeah, in a banana, you see, or every couple of seconds, there's a nuclear decay reaction that will produce a positron. Although this positron, it can never get out of the shell of the banana, if you want. It meets an electron very nearby, and it evaporates, it disappears. Do we have any questions so far? Okay, so now we have the whole array of particles that we need to build a bit. Oh, there's a question. We can't hear you. At least I cannot.
Okay. Is antimatter the same as dark matter?
No, we'll talk about dark matter right now. So,
okay.
But that's an excellent question. Yeah. So antimatter has nothing to do with dark matter, as far as we know. And as we know, the universe is mostly made of regular matter, and there is very little antimatter around. And that's actually a question that we don't completely know the answer for, why there is so much normal matter and so little antimatter. But we'll talk about dark matter right now. So before we talk about dark matter, we need to understand why things move in circles. So we know that if we are driving a car and we're trying to turn, or we're trying to drive a car basically in a circular road, there is a force that pulls us to the center of that circle, which is given by the friction of the tires with the road. So there is always a force that points to the center of the circle, and that basically would keep us driving around. So we can experience that that's true, because if the road is icy, then this force that's pulling you to the center disappears, and then you can no longer run in circles. You would basically skid out of the road, right? So in a way, you can see that the stronger the force is towards the center of the circle, the faster you can drive around, right? So the more grip your car tires have, the faster you can drive in a circle. And if that force disappears, then you are no longer driving in a circle. You will run out of the road. So basically, things move in circles because there's a force that pulls them to the center of the circle, right? So what does this have to do with dark matter? Well, we know that we can look at galaxies, and we know that galaxies are basically rotating around the center of the galaxy. So when we look at a galaxy, we're seeing a whole bunch of stars, and we see that these stars are rotating. Now, we can even measure the velocity that these stars are rotating, because when an object is moving towards us, or when a star, if you want, is moving towards us, we see that this star looks a little bit bluer than it would. And when the star is moving away from us, we see that this star would look a little bit red. So if I look at a galaxy and this galaxy is rotating, I would see that one side of the galaxy is blue because all the stars are moving towards me. And I would see that all the stars on the other side, they would look red because because all those stars are basically moving away from me. And by the amount, or by how blue and how red these stars look, I can measure the velocity of the stars as they rotate in the galaxy. And this is what we have here. So if I measure the velocity of the stars that are rotating in a galaxy, I measure that as I move out from the center of the galaxy, the stars appear to be going faster and faster and faster. And that's a little bit of a surprise, because we know that the reason why stars rotate, or why the star is rotating around the center of the galaxy, is because of another force that we haven't talked about yet, which is the force of gravity, right? It's the same reason why the Earth moves around the sun. The Earth moves around the sun because the Earth feels the gravitational attraction of the mass of the sun. So the stars, in the same way, if you have a star that's orbiting around a galaxy, around the center of a galaxy, it feels, if you want, the mass of all the stars that are at an inner circle of this galaxy. So by looking at the curve and seeing how fast these stars are rotating as I move away from the center of the galaxy, I can calculate, if you want, how much mass there is inside of the circle that this star is doing, right? And what I see is that I have another way, if you want, to measure how much mass there is in a galaxy, which is that by now we know stars pretty well. And we know the masses that stars have, and we know how bright stars are as a function of their mass. So basically, I can just look at a galaxy and convert the amount of light that I see into mass, because I know that all this light that I see is largely due to stars, and I know how stars shine. So if I were to say, well, all the mass in this galaxy is just the mass of the stars that I see shining, I would expect that once I'm moving out of the outer skirts of the galaxy, the velocities would start to drop, because I wouldn't have more mass inside of this galaxy. On the other hand, what we see is that as we go out towards the outer skirts of the galaxy, the stars seem to be rotating faster and faster, which means that there is a lot more mass in this galaxy than the mass of the stars that I see, right? So if I calculate how much mass there is that I don't see, we find out that 80% of the mass on any given galaxy is mass that we don't see. It's not in the form of stars, it's not shining. So that's why we say that 80% of the matter in the universe is dark, and that's why we call it dark matter. There's no other mystery. We know that it's matter because we see it because of the gravitational interaction that it produces. We know that these stars wouldn't be rotating this fast if there weren't a lot more mass in this galaxy than the mass that we see. And we know it's matter because the way we see it, it's because of its gravitational attraction, but it's dark. We don't see it shining, so therefore it must be dark. Are there any questions so far?
Well, here's an old question about the bubble chamber reaction, and where the different particles come from and go to. Mm-hmm.
So basically, what we see here is this gamma here. It's basically telling us that there is a photon, and the photon doesn't leave a track in the bubble chamber, so it's kind of an invisible track. And what we see here is that this photon interacts with an electron, right? So this photon comes in, we don't see it, but we know it must be a photon, and it kicks an electron inside of this bubble chamber. So this electron, basically, like if it was if it were a collision between two billiard balls, if you want, the photon hits the electron, and then this electron that was just sitting around at rest, it gets a kick, and then it goes out this way, right? So this is the interaction that you see here. Now, this photon had enough energy that when it kicked this electron, at the same time, it had enough energy to produce a pair of another electron and a positron. And that's allowed, if you want, because it's this additional energy is generating a negative charge and a positive charge. So it's not changing the total amount of charge that you have in the system. So it's kind of allowed as long as you have enough energy. If you have enough energy, you can always create a pair of a particle and antiparticle. And because they are kind of the opposite of each other, you are not breaking the rules. So you can still do that. So that's what these two tracks here are. So this is the additional electron that was generated, and it basically loses speed, and then it basically thermalizes and goes back into the gas. And then the positron does the same thing, but again circling in the opposite direction because it has a positive charge.
Sorry, I posed one of the original questions, but the original electron is invisible for some reason, and now it's visible after the collision.
Yeah, so the original electron is not visible because it doesn't have kinetic energy. It's just sitting around without energy, so it doesn't produce a track in this bubble chamber. So only the particles that are moving fast, if you want, they would produce a visible track in the bubble chamber. The only reason why you don't see the electron at first is because it's just lying motionless.
Okay, that makes sense. Otherwise, it was violating charge and whatever lepton number, whatever needs to be balanced. Thank you.
Excuse me, I just wanted to tell a very quick story from the world of dance about there's a quite famous dancer named Hanya Holm, and part of the technique she practiced included spinning for a really long time, sort of like dervishes, but in one spot. And she decided to see what would happen if she turned her head. And speaking of kinetic energy, it broke the path of her spin, and she roared out of the circle in a big arc and literally ran to a wall and broke her nose. So this is a really powerful force here that we're dealing with. Thank you.
Yeah, that's absolutely right. You cannot mess with kinetic energy and angular momentum, and if you try, there's usually bad consequences. Yeah, thanks for the story.
Manel, we have a question from Rob. Why isn't the missing mass assumed to reside in a massive black hole at the galactic center? Very
good question. So that's partially true. There is a very big black hole at the center of pretty much every galaxy. And we know that these black holes, we can weigh, if you want, these black holes by looking at how bright they are. So black holes, at least a fraction of them, they are actively swallowing gas. And when they actively swallow gas, this gas heats up and it shines mostly in X-rays. So when we look at these galaxies, so this picture that you see here is a picture taken with visible light with a regular telescope. But if we were to look at a similar galaxy in X-rays, we would see that the stars, they barely emit any X-rays, but the center black hole, it's usually pretty bright in X-rays. And we can measure the mass of this black hole by looking at how bright these X-rays are. And the mass of this central black hole that we can measure to a certain level of precision is much, much smaller than the amount of mass that you need to explain this rotational curve. And we also know that the mass that we need in order to explain this rotation curve, it has to be distributed along a very kind of hazy, what we call halo, around the galaxy. So it's not mass that is just all dumped to the center of the galaxy. That wouldn't explain this rotation curve. We know that it's mass that's distributed pretty evenly and in a somewhat hazy cloud that actually extends way farther than the stars in the galaxy. So we know that the stars in the galaxy, they are confined to this in this structure, but we know that the dark matter, it would fill a larger volume around the galaxy.
A very short question, sorry. I have seen this picture a couple of times. Does that curve, the actual curve, ever flattens and go down? I mean, do we have the continuation of this curve following the regular Newtonian physics or not?
Well, the problem is that, so in order to measure this curve, we need stars, right? So as you see here in this picture, at some point you don't see more stars. Okay. And even though the dark matter keeps rotating at the speed that we would expect, we cannot trace it because we don't see it. So we can only measure this curve reliably wherever there are stars. So whenever the galaxy runs out of stars at the edges, that's how far we can measure. We can still go a little bit farther, and that's actually what you see here in blue, by looking at the gas. So there's gas that extends a bit farther out than the stars, and this gas it has some temperature, and because it has some temperature, it emits photons, it emits radiation. So we can go a little bit farther than the stars by tracking the gas, and these are these blue points here. But again, once you run out of gas, you run out of measurables, you run out of things that you can measure to measure this rotational curve.
You really need a probe for dark matter.
Sorry, go ahead.
You really need a probe for dark matter itself.
Exactly. So we need a way to be able to see this dark matter. We need to make it not dark in a way. So we need to find a way to see it, which is actually what I'll talk about in the last 5 minutes.
Thank you.
So what are ways that we could try to think about in order for us to be able to see dark matter? And as I mentioned in the title of my talk, one way is to try to make use of antimatter. So we talked about antimatter, and we said that if we have a positron, which we have here, which is the antiparticle of the electron, this positron, if it meets an electron, it will annihilate. And what does it mean, annihilate? It means that the electron and the positron, they disappear, they are no longer there. And instead of this positron and this electron, because we need to conserve energy, there are two photons, two particles of light that are emitted. And these particles of light, these photons, they have the particular property that they have the same energy. They have an energy that basically is the same as the mass of the electron and the positron. So the mass of the electron and the positron is 511 keV, which again, it's a unit for energy, but it's kind of also a unit for mass. So in this unit, about 1,000 keV, 1,000 kiloelectron volts is more or less the mass of a proton. So this positron and this electron, when they meet each other, they produce a very particular signature, which is two photons, two particles of light that have a very specific amount of energy. And this energy is in the X-ray or gamma ray range. So it produces basically two gamma rays of a very particular amount of energy. Now, when we look at the sky and we look just for photons from this very particular energy, and when we look towards the center of our own galaxy, we see this cloud of emission. So we know, and here you see an even better picture of it. So towards the center of our galaxy, there is some source, or there's positrons here at the center of our galaxy that are annihilating, producing these gamma rays of very particular energy. But we see that this emission is kind of fuzzy. It's hazy. It extends way beyond the center of our galaxy. So typically, when astronomers, when we look at something in the sky and we don't know where it's coming from, so if this is basically a map of the positrons on our galaxy, and we don't know where these positrons are being created, what's the source of these positrons, what we would do is we would compare it with the maps of things that we know. For instance, if I look here, this is a map of our galaxy in visible light, in the light that we see. So if I look at the sky, I see the Milky Way. And how does the Milky Way look? Well, it's brighter towards the center of our galaxy. And then it's sort of a stripe in the sky. And it's a stripe in the sky because it follows, because our galaxy looks like a disk. So we're looking through this disk. So along the disk, which would be on this axis, we see bright emission from stars. And then when we look away from the center of the galaxy, we see less stars, right? So basically, could stars be producing these positrons? Well, not quite, because what we see is that the disk is much narrower than this broad blob of positrons that we see. So there's other, we can also look at the galaxy with other wavelengths. So we can look at the galaxy, for instance, in radio. And in radio, what we see is basically cosmic rays that are circling around the galaxy following magnetic field lines. And this produces radio emission. So could these positrons be produced by cosmic rays? Well, again, not quite, because we see that this map is also not very similar to this map. So this positron emission is broader towards the center than what the cosmic ray distribution in our galaxy is. And we can keep looking at other wavelengths. For instance, if we see here, this is another nuclear line, which we trace with very massive stars. So we can look at our galaxy at a certain gamma ray band, and we can see where star formation is happening. So maybe not all stars are producing positrons, but maybe just the new stars that are being born are producing positrons. But again, we see that this map doesn't quite look like this one. So what is the only thing that we know that could follow more or less this hazy distribution, that could explain where these positrons are coming from? Well, dark matter could be it. Because we know, so this is a simulated distribution of, or a simulated map of how the dark matter would be distributed in our galaxy. And for what we expect, again, from looking at the other galaxies and seeing the rotational curves, we see that it would look more or less like this. It would look bright in the middle and then fuzzy around the middle in a much wider sort of halo-like structure. So basically what we need to do if we want to try to understand this is we need to try to take a better picture of where these positrons are. And we can even try to map a little bit what is their speed distribution. So how fast are these positrons moving, so that we can try to understand if these positrons could be coming from the dark matter in our galaxy. So there's some models of dark matter where dark matter would annihilate. And in this annihilation, they could produce these positrons that we see. So basically, by mapping the distribution of positrons in our galaxy, by mapping the distribution of this antimatter, this antiparticle of the electron, we can see if this map ends up looking like the dark matter distribution in our galaxy. So how do we do that? We do that with gamma ray detectors. So this is a gamma ray detector that we are developing in my lab. So it's a germanium detector. So germanium is similar to silicon. So it's somewhat similar to the silicon that's in the cameras of your digital cameras or your cell phones. But it has but it's a heavier element, and it's therefore better to stop gamma rays. And the good thing that germanium has is that it can tell us the energy of the gamma rays very precisely, so we can isolate these electrons that come from annihilation of so these photons that come from annihilation of positrons very well. So we have here one detector, and our goal is to basically build an array of 7 such detectors and try to use it to make a map of the positron emission in our galaxy. So there is just one piece of this puzzle that's missing. I'll go over it in a second, which is that if I have a germanium detector, well, that's great, but I still don't have a telescope. So in order to have a telescope, we know that in order to have a telescope, I need some way to focus the gamma rays that are coming. And I know that gamma rays are not very amenable to be focused into anything because they carry a lot of energy. And we don't talk about, or we're not very familiar in our everyday lives with gamma rays. We don't see them very often, but we do see X-rays when we go to the doctor to take an X-ray, and we know that X-rays it's very penetrating radiation, so it doesn't let itself be focused very easily. So how can we focus gamma rays? The answer is, well, we can't. There is no easy way to build a lens that would focus gamma rays. So how could we take a picture of the sky in gamma rays? And the way we propose to do that is by doing something that we call the occultation technique. So imagine that I put my germanium detectors in a satellite, and then I make this satellite circle around the moon. So if the satellite is circling around the moon, then again, my detector only sees, oh, now there is a gamma ray, now there is no gamma rays, but it doesn't know where the gamma rays are coming from. So I cannot make a map out of that by itself. But if I have it circling the moon, then imagine that there is a gamma ray source somewhere here. And then as the satellite goes behind the moon and loses sight of this gamma ray source, then the amount of the count rate, the amount of gamma rays that my detector sees would immediately drop, right? At the moment when the detector goes behind the moon, then it's not going to see this gamma ray source anymore, so the rate would drop. And then as the orbit continues, at some point, the satellite would emerge from behind the moon and would see the source again, and then you would see that the rate, the amount of gamma ray events that I see would immediately increase again. So basically, if you put a detector in orbit around a celestial object, we can map these changes in rate, these changes on the number of gamma rays that we see at any given time with directions in the sky. And therefore we can make a map, even if we cannot build a lens that can make a gamma ray telescope. So basically that's what we're trying to do. We're trying to make better gamma ray detectors and then arranging them in a mission that is able to give us a map of the positrons in our galaxy, and hopefully eventually learn what the dark matter particles are. So I think that's all I had, and I'll take any questions. Thanks.
Hands up.
Yes, I've got a question. So you have to, in order to carry out your experiment, you'll have to point that thing at like almost an infinite number of points in the space to get a whole view of what you, or I guess maybe the flatness of the of being in the would allow you to cut down the number of different positions you need to get.
Yeah, no, so you're absolutely right. If I had a classical telescope, I would need to point it at every position in the sky to get a full map. But what I'm saying is, so my detector is not really a telescope. I cannot point it anywhere. It's just basically, it's like a block that detects gamma rays no matter what direction they are coming from. So you get the imaging capability and you get to cover the whole sky, but basically having it orbit a celestial object and then doing this mapping of the different detection rate of gamma rays to the objects that are behind the moon in this case at any given time. But the thing is that, so when you put a satellite in orbit around an object, it's not always orbiting on the same plane, but it does what we call orbital precession. So slowly, by orbiting the moon several times, you would basically end up mapping the whole sky if you can keep the mission going for long enough time.
So my question was why the moon? Is just because the radius is adequate? Why not Earth? It would be cheaper. Or can you send it to an asteroid?
You're absolutely right. So the moon is more expensive. So that's a disadvantage. But why is the moon better than the Earth? And the reason is that the moon doesn't have an atmosphere, and the Earth has. And why would an atmosphere bother us? It would bother us because in the atmosphere, so we know that there's cosmic rays, protons, very energetic particles that are constantly hitting the Earth. And in the atmosphere, they basically, these protons, they break down and they produce what we call a particle shower. And in this particle shower, unfortunately, there's going to be a whole bunch of positrons being created. So if I look at if we look at the Earth, the atmosphere of the Earth is kind of glowing in positrons in a way. Mm-hmm. So it would be what we would call a background, a source of background. So it would basically make for a very noisy measurement. On the other hand, the moon doesn't have an atmosphere, so it doesn't have positrons lying around. So then we know that what we see are really astrophysical sources of positrons and not local positrons that are being created around the moon. Those would be very much smaller number than if we were to do this on Earth.
So on Earth, you would have, even if you go very far away, you would have some kind of profile in that decay that, with lots of noise. Now, what about the smaller object? An asteroid would move too fast or would be difficult to connect to, or?
It's again a matter of cost. So the Earth is the easiest thing to put something in orbit to, but it's not very well suited for our experiment. So the next cheapest thing is the moon, and the moon works just perfectly fine. So yeah, if we were to put it in another object, it would be just more difficult to do.
Thank you.
Another question, please. If there's, and I know you probably can't answer this maybe, but if there's so much of this dark matter around, how come it doesn't mess with our lives at all? Like interfere with me getting a cup of coffee, all this dark matter crashes into my coffee cup. That's
an excellent question. So we know, so we talked about forces, right? So we talked about the electromagnetic force. We talked about the strong force. And we know that dark matter, well, what are the properties of dark matter that we know? We know that it's dark. Because it's dark, we know that we can say it's cold, because anything that has a temperature, it emits some amount of light. So the fact that it doesn't emit any light, we know that it's cold. But we also see that, or we don't see any evidence of it other than the fact that it has a mass and then it's there. So we know that whatever particle is making up for the dark matter in galaxies, which we don't know which particle it is, it has to interact very weakly with the rest of the particles that form the standard model. So we probably have millions of dark matter particles going through us every day, but they interact with normal matter only very, very weakly. Only once in several millions, a dark matter particle will interact with a normal particle and actually do something that you would notice. So that's why we can go on with our lives, even though there's probably a whole bunch of dark matter lying around. We don't see it because there's no interaction that would make dark matter interact with normal matter and produce something noticeable. So let me see. So John Ebert has a question.
Is the distribution of dark matter thought to be clumpy like the stars and the galaxies, or to be distributed evenly throughout space, even between the galaxies? Or is it thought to be clumpy in the same sort of general location as regular?
You're unmuted.
Yes.
So I don't.
So
Yeah.
that's a good question. So for what we know, dark matter is pretty much distributed
I think you can just
around where normal matter is, but it's just more fuzzy because because of this very weak level of interaction. So for what we know, there is dark matter in galaxies. There is probably less dark matter in between galaxies. So you would say that dark matter more or less follows. So wherever there's normal matter, there's usually dark matter, and wherever there's no normal matter, there's probably less dark matter. If that
I think
answers.
you can just speak up, I guess.
Okay.
So I'm just going by order here. We have Jeanette. Was there a question?
Can you hear me?
Yes.
Has anybody ever looked at making these calculations, assuming that the answer is not dark matter, but that we have less mass in the universe than normal general relativity would predict, and trying to explain this phenomena in that manner? Or are there too many contradictions in other theories?
There are ways to try to explain the rotational curves of galaxies that don't involve dark matter. And for instance, one of them is instead of assuming that the amount of matter that we see is wrong.
Sorry,
Instead of assuming that the amount of matter that we see is wrong, some theories assume that the theory of gravity that we have is wrong. So because of the force that makes these stars go around is the force of gravity. If there is something wrong in the way we understand gravity, then the rotational curves would be different. So there's alternative ways of explaining these rotational curves that do not involve dark matter, but that involve, for instance, modifications on the theory of gravity. But there's also other pieces of evidence for dark matter, such as gravitational lensing. So basically, the curvature of light around mass that make this modification of gravity a less appealing explanation than dark matter itself.
Thank you.
When would this experiment fly, the moon experiment? Do you have an idea if it'll fly anytime soon?
Probably not anytime soon, but hopefully not. So usually this goes by stages. So the stage that this is at a stage where, so usually if you want to do something like that, you go to NASA and ask for money. So far I went to NASA and they gave me money to develop the detectors. So that's at the stage where we are at right now in our lab. We're basically building the detectors that would go into this mission. Now in a year or so, I will go back to NASA and I will say, hey, now I build the detectors. I wouldn't ask for a mission directly. I would say, well, now maybe can you give me some more money to, instead of having just one detector, put 6 of them, and then maybe not fly them to the moon, but maybe just fly them on a balloon so that we can test that everything works out okay. So that would probably take another 4 or 5 years. And then when we say, well, now we built a detector, we put it on a balloon, it works well, it can measure what we want it to measure, then it would be the time to say, well, now can you basically give me a ride to the moon and put it in orbit? So the timescale for that would be probably 10, 15 years. And it's still every step needs to work out, right? But that's more or less how this works out.
Thanks.
Jeanette, did you have a question? Another question?
No, I finished my question. Thank you.
Okay, there are a couple of questions.
I have another. Oh, I'm sorry.
Go ahead.
I have another question about this experiment. It looks like you are using some kind of triangulation to replace focusing. That gives you better resolution, but that would depend on the distances that you are using. So you have a range of possible gamma ray sources at some range of distances that you can see better this way or not?
So the resolution actually on this occultation technique, it basically depends on both how bright the gamma ray source is. So we can only detect relatively bright sources. And in a way that's related to distance, right? Because the farther a source is, the weaker it will appear. And when a source gets very weak, basically the jumps in the event rate will be so small that we cannot perceive them anymore.
Yeah.
So it depends on how bright the gamma ray source is. And it also depends on how big your detector is. So if your detector is bigger, you will detect more photons. So it will be easier to see changes in the amount of photons that you see at any given time. So the bigger the detector is, if you want, the better resolution you have, because you can see smaller drops in the event rate. As far as distances goes, I think it will be very unlikely that we would be able to see positron sources outside of our own galaxy, because they would be very far and they would be very weak. So the goal would be just to map sources of positrons inside of our own galaxy. So for instance, if there's a nearby pulsar that's producing an excess of positrons, that's what we would hope to see. We would also hope to map the positron distribution towards the center of our galaxy, but it would be very unlikely that we can go beyond our own galaxy with this kind of experiment.
So for doing a cosmological probe, you need gigantic detectors. I mean, if you want to see what happened in the early universe or earlier universe, it's not this technique.
It wouldn't be with the positron emission.
Yeah. Thanks.
So Jonathan Daner had an intuition that the physics of all this has something to do with the physics of a PET scanner, positron emission tomography, and wondered if you could explain that connection.
Yes, that's an excellent question. And in a way, sometimes I've tried to sell this experiment as trying to make a PET scan of our galaxy, because this is pretty much what we are doing. So how does it? Oops, what did I do? Well, I lost the slides, but let's go without slides. So how does a PET scan work? So a PET scan works basically in a somewhat similar way. So when they put you on a PET scan, you are basically surrounded by gamma ray detectors, similar to the ones that I showed you. And what they do is they would inject you with, for instance, a sugar molecule that has they've replaced a fluorine atom by a radioactive fluorine that produces positrons in the same way that I said that the potassium in a banana produces positrons. So if they inject you with some with a sugar that's stacked that produces positrons, then of course any part of your body that's very metabolically active, that it's basically eating up a lot of sugar, all this radioactive sugar will go there, and then the positrons, whenever they are emitted or whenever they are produced in whatever organ it's eating up all this sugar, they will produce a positron, and this positron will immediately find an electron and will annihilate. Now, to conserve what we call linear momentum, the two photons that are produced in this electron positron annihilation, they are exactly back to back, right? So if I have a giant gamma ray detector that's surrounding me, I would see that two detectors that are at opposite sides of me would get a hit whenever there's positron emission. So, but basically by looking at where these hits are around your body, you can make a map of where this radioactive sugar went. So you can basically know where your body is metabolically active in an elevated way. I don't know if that was a decent explanation, but that's as far as I know how a PET scan will work.
Oh, here's another question from John Ebert about what is the highest energy photon we have detected, and what's a higher energy than gamma rays?
Yeah, so it's so difficult to see photons with energies larger than what we call gamma rays that we haven't even bothered giving them a name. So everything that's above X-rays that has energies higher than the energy that an electron has, We just call them gamma rays, no matter how high the energies are. Now, the highest energy photons that we see, they are probably about 10 billion times the energy of a visible light, right? So the light that we see has energies of about 1 electron volt, we would say. That's the unit that we use. So the highest energy photons that we see, they have about 10 billion times that energy. And those are higher energies than the ones that I was talking about. So I was talking about gamma ray photons with energies of about 1 million times more energy than visible light. And the highest, they go about 10,000 times higher than that. So I don't know if there's, I'm happy to stick around for anyone who wants to ask more questions.
Looks like Al Holter has a question.
Yeah, Al, do you want to go ahead?
Yeah. Can you hear me?
Yes.
I have two questions. First of all, you refer to the dark matter as a halo because it extends beyond the stars. But is it of equal density in the midst of the stars?
That's a very good question. So we call it a halo, but we still, for what we know, it is denser around the center of the galaxy where the stars are, and it gets fuzzier, if you want, or less dense as you move out from the center of the galaxy. So it still has a wider reach than the visible matter, but it kind of diffuses away. It becomes less and less dense as you move away from the center of the galaxy.
So it presumably imbues the solar system.
Oh, yes. Yeah.
It's all through.
Yes, and actually
Okay.
I didn't talk about it, but there's also a very active field of research, which is what we call direct detection of dark matter, which is basically trying to exploit sort of the thing that we said, that matter is very weakly interactive, but we hope that it has to interact in some way with regular matter. So people put giant detectors just in hopes that one of the dark matter particles that is going through the solar system and it's going through us, it will interact with the normal matter and will produce a signal that we would be able to see. So that's
Thank you. I have another question.
Go ahead.
I missed the connection. Suppose you could measure the antimatter as well as you like. How would that exactly tell you, and what would it tell you about the dark matter?
Yeah, that's an excellent question. So basically, the way you would go about knowing whether the positrons are due to dark matter or not is basically by eliminating every other possible explanation. So you first say, well, what do we know is in our galaxy? Well, we know that our galaxy has stars. Does the map of positrons look like the map of where the stars are? And then you say, no, then it cannot be stars. Then we go for the next possibility, which is, could pulsars be the place where these photons are originating? And then we basically have a map of pulsars. We would have a map of positrons. We would see how well they match. And there's also information about the energy and the velocity that these positrons have. So in a way, basically, you would only guess, or you would only have some certainty that it's dark matter after eliminating all the other possible suspects. And that's basically, so we're somewhat halfway through. We have a decent map of positrons that allows us to eliminate most of the possibilities, but we still need a better map to be able to completely rule out other possible explanations.
Thank you.
One last question. Rob Dickhouse asked, is there a global agreement concerning satellites orbiting the moon? If not, it seems like now is the time to put one in place, because the moon's orbit could get cluttered the way the Earth's orbit has become cluttered with space junk.
Yeah, so that's an excellent point. And as far as we know, we have only very loose agreements of what can go around the Earth, which would be even a bigger worry than the moon. So I think these international agreements, they are very difficult to come up with. But there is now, and I mean, another reason why we're proposing for this to go around the moon is because there's now a push to put more scientific equipment, if you want, on the moon, and the US is basically trying or planning this Artemis space station that would basically be similar to the space station, but would be orbiting the moon instead of the Earth. And it's been kind of agreed that the way, or to go to Mars, the first step would be to go back to the moon. So there are definitely going to be more satellites and more scientific equipment going in orbit around the moon, but I don't know what the plans are for regulating that, and I assume that there aren't many, given how unregulated space around the Earth is. But it's an excellent point. It would be good to.
Thank you. I just had a PET scan yesterday, and now I very much have a better clue as to what was actually done yesterday. So thanks for that segment. And David Brown, thank you very much for my congratulations.
Thanks. I'm glad it helped to figure out that medical procedure.
Science Saturday rules.
So I see Steve has a hand up.
Yeah, thank you. I don't have a good physics question because those are hard, but I have a psychology question. Is it hard to do this work when you think that, in the time frame you just explained, that you may not get answers for 15 years or more, and you got to trip over a lot of bureaucracy in order to get there? That must be difficult.
You are right. There is a lot of uncertainty in the type of work that we do, but I guess it gets compensated by how exciting it is. So even though I know that this mission that I just talked about, it's probably 15 years away or more, it's so exciting to just go in the lab and see that the detector is working as you expect, and then you build the next stage and you try to put two detectors working together, and you see that they work together well. And in a way, it's not that only at the end you get a final answer, because we're basically right now, maybe we're not learning about positrons and dark matter yet, because we need a huge investment in order to do that. But we're learning how to build better gamma ray detectors, and that starts the moment you start the development. So I would say, of course, the final prize is the most rewarding, but there's a lot of very interesting science happening while you are developing these ideas into something that would give you the final answer. So,
probably the problem is much worse for people that are older. I remember Kip Thorne saying when he was here that he expected to live up to 140 to see, the results of some of his experiments.
Well, perhaps it helps if you have stimulating colleagues too.
Oh yeah. That's also, I mean, colleagues and students and people working with us. It's always very exciting to just go to the lab and talk to brilliant students and have good colleagues, and we have collaborations that extend beyond just our university. But yeah, no, that also makes this job as good as it is.
I got a question, like a couple questions real quick, can I?
Yeah, please.
Okay, one, why can't you build the telescopes like the Chandra, where you have a grazing incident, series of cylindrical lenses? And the other question I saw talk last week from the astronomy club suggesting dark matter might be consist of tachyons. What do you think about those ideas?
So tachyons, I mean, I'm sure there's ways where people have thought about how tachyons would be particles that move faster than the speed of light.
It's the source of dark matter, yeah.
Yes. So I'm sure people have thought about how tachyons could explain that, but I'm not familiar with those theories. So I wouldn't know.
Okay.
I wouldn't know. And you had an earlier question.
The other question was, when they built the Chandra X-ray scope, they used cylindrical lenses with grazing incidence where it hits at a low angle. Why couldn't you build a gamma ray telescope using that same sort of using cylindrical lenses?
Yes. So grazing incidence, it works great for X-ray optics. And X-ray optics would go, so I talked in this units of energy that we use, I talked about 500,000 electron volts. That's the energies of the photons that we care about.
Right.
You can build grazing incidence optics all the way up to about 80,000.
Okay.
It would be 80 compared to 500. The reason for that is that the way the grazing incidence works is that you coat your lenses with a material that has a very high atomic number, a very high number of protons. But these atoms, they also absorb X-ray light at the same time as they reflect it.
Oh, okay.
So the best material that we know to make these cylindrical grazing incidence lenses is iridium. But iridium has a very sharp absorption edge at 80,000 electron volts.
Oh, okay.
So beyond that, there are some techniques, but grazing incidence doesn't work anymore.
Okay, thanks.
So I see Boyd.
Yeah.
Yeah, go ahead.
Two questions. One, in the bubble chamber image, why do the two curves from the electron and the positron look not quite symmetric? And the second question is, I assume that we can neglect all the mass of all the neutrinos that have ever been emitted, right? That can't possibly contribute to the missing mass.
Mm-hmm. So the reason why the two particles were not exactly maybe I should try to bring that back up. So I'm having trouble sharing the screen, but let's try this. Okay, so actually, yeah. So why don't they look exactly the same? And I'm gonna have to guess maybe it's because so one of the two, probably the positron, got a little bit of a higher amount of kick in when it was created. So the fact that the circle of the positron looks a bit wider, if you want, than the circle of the electron, it means that it was moving a little bit faster at the point when it was created. So if the reaction had been only a photon producing a positron and an electron, they would have to look exactly symmetrical. But here it's basically a three-way collision, if you want, between a photon, the electron, and the pair of positrons and of electron and positron. So because this is a three-way collision, then the positron and the electron, they may not be exactly symmetric in the amount of energy that each of them takes, but they have to share energy with the electron that was emitted. So it looks like maybe the electron here and the electron here, they took a little bit less energy than the positron here. That would be my guess about why they don't look exactly the same.
And then about the neutrinos?
Yeah, so the neutrinos, that's an excellent question. So we said neutrinos, which are here, they are very weakly interacting, so same as dark matter, but they have very little mass. So we've been able to measure the mass of the neutrinos, and we see that they couldn't nearly add up to the amount of mass that is missing from galaxies. So basically, they are in a way dark matter because you don't see them, they don't interact. They interact only very weakly with the rest of matter, but they weigh too little, so they can't explain. They are just too light.
Oh, thank you.
So I see I lost my participant list. Yeah, but I see. So Liliana has a question.
Yeah, talking about neutrinos make me think in which way dark matter is so little interacting, and does the amount that we have to have and how little we know, I mean, how little interacts, somehow can we predict in which range of energies we will find the masses of these whatever particles, or do we have ranges for searching and so on?
There are, so basically the way this works is that, so there are some theories of basically how nature is organized that we would call that are beyond the standard model. So we know that, so in this picture that I have here, which is all the particles that we know are there in the standard model, there's no dark matter particle, right? So any theory that brings up a particle that could be dark matter, we would call it beyond the standard model. And these theories, they make predictions. So they can predict what range of masses would this dark matter particle have. They also predict how this dark matter would interact with normal matter. So for instance, at the Large Hadron Collider in Geneva, we're basically smashing very energetic protons against each other, and then all sorts of different particles are created. And what's being done is that usually you try to bring more and more energy into these collisions. And the fact that we don't see any particle that could be dark matter from these collisions, it basically tells us, it pushes the mass of the dark matter particle up. So by not seeing any strange particles in the Large Hadron Collider, you're kind of pushing the mass range of this dark matter particle up, because otherwise you would expect it to show up there in some kind of surprising way that we don't see.
Now, the amount that we need to compensate for the rotation profiles and so on, does it give you another bound on?
I don't think that gives you a bound so it only gives you a bound on the total amount of dark matter, but you don't know.
You don't know how many particles you have.
Exactly. So you cannot count them.
Yeah.
You cannot count them, so you don't know how massive they need to be.
Yeah. Thank you.
I have one more.
Yes, please.
The Higgs boson is thought to give mass to normal matter. Is it the same sort of relationship to dark matter, that Higgs boson is involved with dark matter in the same way it's involved with normal matter?
I don't know. I don't know if there's any. There might be some. There might be beyond the standard model theories where the Higgs couples with dark matter, but I'm not aware. That's a bit too far out of my expertise.
I know it's been looked at. I think that it's not the most theoretically favored possibility.
Yeah, thanks, Mike. So I have not been looking at the chat. I don't know if there's anything else. Well, yeah. So thanks everyone for joining. I hope it was a good way to spend Saturday morning. It was definitely a great way to spend a Saturday morning for me. So I'm glad I got to do this.
Thank you. Very entertaining.
Thank you.
Thank you.
Thank you.
Thanks, everyone.
So thanks for doing this, Manel. It was really good. you know, you've done this before, I think, and the range of questions is just really, really large.
Yeah, yeah, it was really exciting. Yeah, and thanks for helping out managing the questions and
Yeah, there were a lot of questions today. It was good.
And the audience. Yeah, no, this was fun. Yeah, happy to do it again whenever it's time.
All right, great. All right, thank you all. Thanks, Manel.
Thanks everyone.